Hello everyone and welcome to the 7th lecture in the Automotive Engineering Fundamentals course, MEC 3430. Today I'm going to talk about electric and hybrid drivetrains. So last class we looked at automatic transmissions and other drivetrain components. This included torque converters, the transmission itself, drive shafts, final drive, and finally differentials. So in this lecture we're going to look at electric vehicles, hybrid electric vehicles, and then kind of an offshoot of that, which is fuel cell vehicles. Okay, so what are electric vehicles and what are the different classifications? So EVs consist of a class of vehicles that use electric motors and batteries as either solely or part of the propulsion system. So there's BEV, or battery electric vehicles. They have no internal combustion engine and are charged via external source. So there's a plug. So this is essentially we have to plug in our car at night to give it charge so they can run the motor, electric motor, I should say. There's hybrid electric vehicles, HEVs. These have an internal combustion engine but cannot be charged externally. So in this case, the battery in HEVs can only be charged through excess power from the internal combustion engine. Then there's plug-in hybrid electric vehicles. They have an internal combustion engine and can also be plugged in to charge the battery. So these type of vehicles have kind of the ultimate flexibility. You can either charge them from the wall or the battery can be charged from the internal combustion engine when there's excess power. Now, why are we talking about electric vehicles? Well, they're becoming popular due to rising fuel costs and also pollution concerns or concerns over climate change. The thing with an internal combustion engine is no matter how efficient you make it, it's always going to emit carbon dioxide. That is the main component, one of the main components other than water from combustion. You can't get around releasing carbon dioxide when you burn a hydrocarbon fuel. And carbon dioxide is the biggest contributor to climate change. So you can see how no matter what we do with internal combustion engines, we're always going to be emitting this carbon dioxide, and that's a problem. Now for electric vehicles, there's always three main components. There's a battery, there's an electric controller or some type of controller, and this connects to an electric motor, which then drives these poorly drawn drive wheels. Not sure, I guess their wheels are trying to hypnotize you, but battery, controller, and motor are the three main components. Now, the battery generally is the biggest issue when it comes to electric vehicles. Electric motors, not really an issue. The controllers, not much of an issue. The battery, though, is the biggest issue. Now, a lot of these issues I'm going to talk about, they have been very significant advances made in the past even few months, if not year. And these issues are always being tackled by either Tesla or the other automotive manufacturers. So here are some requirements for the battery. So it has to be able to maintain a stable voltage output over a wide range of discharge rates, i.e. depending on how much current you're drawing from the battery, basically how much load you're putting on the electric motor, we have to have a stable voltage output so that the motor can have the correct voltage operating range. Has to have a high energy density. This is the ratio of stored energy to mass ratio. Now this is one of the biggest concerns with batteries. When we look at hydrocarbon fuels, their energy density is almost an order of magnitude higher than most batteries used in automotive applications today. This is one of the major issues keeping widespread electric vehicle adoption at bay, is that if you had to carry a battery that could give you, say, 1,000 kilometers of range in a big SUV, it would weigh so much that you would have to have double the size of the electric motor to drive the vehicle. This is one of the reasons why electric airplanes, although there has been a small airplane run purely on electric motors, I actually did a flight in Europe. In order to do a flight over the transatlantic, say, going from New York to, say, London Heathrow in the UK, the amount of weight you'd have to carry from batteries is just astronomical. So high energy density, this is a major issue, although again, companies are continually looking at this and improving it. Now, there are some people who would say that you will never be able to get batteries at a high enough energy density Because if you look at the energy density of, say, hydrocarbons and try to get a solid state device that has the same energy density, you're basically looking at dynamite or TNT that in order to have that type of energy density. So proponents would say, well, even if you got to that energy density, you're basically walking around with something that has the energy content on the same order of magnitude as dynamite. Now, whether or not that means it's going to spontaneously explode, I'm not exactly quite sure, but that is an argument. It has to have a high peak hour power output per mass, so it has to be able to respond to the situation where the driver wants more power and a peak power output. High energy efficiency goes without saying. Ability to operate over a wide range of temperatures. This is a problem in Canada. We have a pesky little season called winter, and also we have the Northwest Territories and the Yukon. Electric vehicles, the range suffers dramatically when it's operated in low temperatures, and this is a problem. Good charge retention, fast recharge times. This is also an issue right now. A Tesla can be recharged very quickly, but only if it's attached to a Tesla supercharger, which has a very high voltage and amperage requirement. I believe it's 240 volts and 90 amps. Most houses are only wired with 100 amps total. So if you were to try to charge your Tesla, you basically wouldn't be able to run a single other thing in your electric device in your house without blowing your main breaker. This is kind of a problem. Ability to withstand over or under charging events. We don't want the situation where if you undercharge it or overcharge it that we end up destroying the battery. Should be maintenance free. This one generally isn't an issue. Should be rugged and resistant to shock, safe during use and during an accident. We don't want the thing exploding like dynamite. It needs to be readily available and constructed from cheap and environmentally friendly materials. This is currently a major issue. Currently, the manufacturer of the batteries, particularly lithium-ion, is not environmentally friendly. The mining process to get the lithium is very bad for the environment. And then once the battery, I guess this is the next issue, is efficient reuse of materials at the end of life cycle. Again, another major issue. When the batteries have to be discarded, they're also not environmentally friendly. There's some debate over whether, because of the use of batteries, whether electric vehicles, the net impact on climate change is actually less because of how bad the batteries are for the environment. Okay, so in other words, the batteries are the main point or thing that is that needs to be improved upon when you're talking about electric vehicles, whether it be hybrid, plug-in hybrid, or pure electric. Okay, so since we said the batteries are so important, what are the main types of batteries that are used? Well, before we talk about the types of batteries, let's look at the three main components. There must be a positive electrode, cathode, a negative electrode, an anode, and an electrolyte. So we have negative and positive plates, which are separated by insulators. And the number of plates influences the voltage, amperage, and capacity. So there are four main types. There's the lead acid battery. This is the type that you'll see under the hood of most normal automobiles. So the positive cathode is a lead dioxide and the negative is lead. There's nickel-based batteries, which have positive cathode is a nickel and then the negative is an iron, zinc, or cadmium. This is actually more common in household or old household rechargeable batteries or normal NiCad batteries. Those are very common for rechargeable batteries at home. And then you have the lithium-based batteries. These are most common in electric vehicles because they tend to have the best performance. When we stated those requirements, lithium-based batteries tend to meet most of those requirements. So the positive is a transition metal and the negative is a lithium. The other types of batteries as well, sodium-based, however, we're not really going to discuss those because they're not as relevant to automotive vehicles. Okay, so what about the electric motors themselves? Now, I don't want anyone in this class to all of a sudden become an expert on electric motor design. I just want you to have a very rough understanding of what happens. Essentially what we have is we have a voltage that goes through a magnetic field where we have a wire that has a voltage applied and it's in a magnetic field, and because of the direction of the current, it opposes this magnetic field, and therefore we get a rotation. So most motors are direct current, although AC motors are somewhat being investigated as well. So actually our own Dr. Carr in the electrical engineering department, he does a lot of research into AC motors, very good researcher. So a magnetic field is generated when electrical power is supplied to the winding / commutator, sorry, I can never say that, through brushes into the armature. So because the stator is fixed, the rotor rotates. So AC motors can be used and have several advantages. They are more lightweight, smaller volume, lower cost, and higher efficiency. However, the issue with AC motors is that the battery is always DC, so we need to have some sort of power inverter to convert the DC power coming from the battery to an AC current. So there's an extra component we need if we design vehicles around AC motors. So that's why AC motors are currently not the most popular for electric vehicles. Now let's look at controllers again, not expecting anyone to be an expert in electric motor and EV motor controllers. This is mostly the domain of electrical engineers. If you haven't noticed, a lot of things to do with the design of electric vehicles is actually more related to electrical engineering rather than mechanical. EV motors can be AC or DC based, but as I said, because of the battery, most are DC based. So the controller is a PCM, or pulse control module. It's similar to internal combustion engine driven vehicles with electronic throttle position. So a potentiometer is used to measure voltage induced by depressing the accelerator. This sends a signal to controller, where its programmed algorithms send electric power to the motor. And the signals sent to the motors are a series of on-off pulses, with the frequency controlling the mean voltage sent to the motor. So it always sends the same voltage during each pulse, but it's just how often it pulses. If it's pulsing 50% of the time, that means the average voltage to the motor is 48 volts. So it doesn't vary the voltage sent to the motor, it varies the frequency of the pulses. And basically the average of those pulses over time gives you the voltage being delivered to the motor, and therefore the power. So talking about pure electric vehicles, what are some disadvantages and benefits? Or benefits and disadvantages. So advantages, there are no or minimal on-road emissions. While you're actually driving the vehicle, there is no on-road emissions. Now, depending on how you generate your power for the electric vehicles, as we discussed earlier, if your power grid uses mostly coal, well, the problem is then you're essentially driving your vehicles with coal, which is much worse than gasoline or diesel. So no or minimal on-road emissions. Electric motors have higher efficiencies than internal combustion engines. This is true regardless of what internal combustion engine or motor you're dealing with. There's also reduced noise pollution. Electric motors are pretty quiet. The first time I heard a Tesla vehicle being driven, I didn't even know it was driving up behind me. I was using a taxi in British Columbia. And I couldn't even hear the taxi approach because it was so quiet because it didn't have an internal combustion engine. What are the disadvantages? High capital costs. It costs more money to buy an electric vehicle. Now, a lot of governments worldwide are trying to offset that cost with incentives or price rebates to encourage people to buy electric vehicles, but governments don't have money, so really they're just putting the bill on other people. They're just kind of taking money from other people to encourage people to buy electric vehicles. So still high capital costs. Long research times, people are still working on that though. Short driving range compared to internal combustion engines. Again, this is also being improved. Limited payload capacity, i.e. if you try to put, now there are some companies such as Ford that are coming out with electric trucks. I'm not sure if they're full electric or if they're hybrid, but if you had a full electric truck, essentially as you load your truck, you're going to drain your battery even faster and have a very low range. Marketing challenges, depends who you're marketing to. There's obviously a group who would love to have an electric vehicle as opposed to an internal combustion engine powered vehicle. But there are some people, like myself, who just like the sound of internal combustion engines, and that's what they're used to. And so trying to convince them to get an electric vehicle is difficult. And the other disadvantage is reduced noise pollution. Now, this is somewhat of a joke. As I said, I love the roar of an internal combustion engine, and unfortunately, you can't get that when you have an electric vehicle. Now, this is not really a technological disadvantage. This is more so related to the marketing challenges. Now, this whole concept of using electric vehicles, this isn't new. Forklifts, if you've ever been inside an industrial plant, they're battery powered. Locomotives for underground mining, if you think about it, if you're underground mining with a bunch of workers, you can't exactly be emitting carbon dioxide and other pollutants into that small confined space, otherwise everyone would die of asphyxiation or choking, basically, or not choking, not being able to breathe. So they have to use batteries or electric motors in that place. And also short distance public transit. If you've ever been into an airport or different terminals, the transport devices are probably electric. Okay, so that was electric vehicles, but what about HEVs or hybrid electric vehicles? So a hybrid electric vehicle is any vehicle that uses an internal combustion engine and at least one other propulsion system with an electric motor. So it can be multiple electric motors, but it has to have at least one. Now, there are two kind of overall types of hybrid electric. There's the series and there's the parallel. In the series, the motor is in line with the internal combustion engine. In other words, you can't have one drive without the other. In the parallel, you have them split so that the motor and the internal combustion engine can work independently to drive the vehicle. Now, if you look at a layout here, here's what a possible layout is for hybrid electric. We have an internal combustion engine, which always drives a generator. So there's no way the internal combustion engine can directly drive the wheels. It's always driving a generator, which always goes to the battery, could then be sent to the electric motor. Now, here we have this power split device. Now, this means part of the electric motor power can go to driving the wheels, or part of it can be gone to driving the generator. So in this configuration, though, we can't ever have the internal combustion engine completely drive the drive wheels, which is potentially undesirable. Whoops. Here we go. Okay, so what are the overall benefits? So the overall benefits are energy and environmental. The first thing is regenerative braking. This is by far the biggest advantage of hybrid electric, is when you're accelerating or driving at a constant speed, your battery is discharging. You brake, and during the braking, instead of turning all the energy from braking into heat, part of it is turned into electrical energy and stored in the battery. So this is actually one of the main energy savings of an electric vehicle, is that you can actually store the energy that you generate from braking into something useful. And this has a huge impact in terms of energy savings, particularly obviously when you're in city stop and go driving. We also can have different fuels that can go into powering the electricity form. So if we look at all the different possible ways that we can power vehicles, we have fuel cell electric vehicles. This is the diagram, figure 12.22. We have fuel cell electric vehicles, which are powered by hydrogen. We have battery electric, plug-in electric, hybrid, and then internal combustion engine. So internal combustion engine, we're only going to power our vehicle via oil or liquid fuels. HEV, we could potentially power our vehicle through liquid fuels and other potential fuels, but mostly it's still going to be liquid fuels. For plug-in electric vehicles, we can either fuel them with liquid fuels or with electricity, and if electricity comes from biomass or other renewable energy sources, that means we have a possible net carbon zero. Particularly for the battery electric vehicle, we definitely have a net carbon zero if we get the electricity from renewable sources, i.e. avoid coal. And obviously, depending on how we generate the hydrogen, you can actually generate hydrogen from liquid fuels or natural gas. So if we generate the hydrogen from liquid fuels or natural gas instead of burning them, that means we're taking the hydrogen from our huge stores of fossil fuels and still making use of those fossil fuels. Now, of course, making the hydrogen from the fossil fuels takes energy, so it's debatable in terms of if it's going to be net carbon or what type of carbon reduction we're going to see, but that's another possibility. If we look at a comparison of global harmful emissions, 12.26, if we go from internal combustion engine vehicle to a hybrid electric vehicle, we see almost all emissions, harmful emissions, are dropped dramatically. Now, even battery electric, well, how could a battery electric be emitting stuff? Well, remember, this is during the entire life cycle, so this is also during the battery manufacturing process. So when you compare hybrid electric to battery electric, now again, this is not looking at CO2 emissions. That's kind of the key thing that is missing from this graph. Obviously, with HEV, you can't avoid CO2 emissions. Battery electric, you could. It seems here that we could reduce our emissions greatly using hybrid electric versus plug-in. And again, if we have a plug-in hybrid electric vehicle, again, we can charge it by renewable energy sources, and we really only have to rely on the internal combustion engine as a backup source. So talked about the configurations. We said series and parallel. So in series, the internal combustion engine powers a generator, which charges a battery and propels the vehicle. So in other words, the generator or the electric motor does all the propulsion. Internal combustion engine cannot directly power the wheels. Parallel, it's either the internal combustion engine or electric motor can be used independently. Series parallel, the internal combustion engine can be used to propel the vehicle and or charge the battery, or the battery can operate in full electric mode. So obviously series parallel seems to be the most flexible. Now when we look at, again, the different types of vehicles, we have battery electric, plug-in electric, plug-in hybrid vehicle, full hybrid, micro hybrid, and then obviously the internal combustion engine vehicle. The proportion of power either coming from gasoline or diesel or battery or the internal combustion engine or the motor kind of depends as you go down. As you go down to battery electric vehicle, obviously the energy source is purely the battery and the propulsion is purely the electric motor. If you're looking at the other end of the spectrum, internal combustion engine vehicle, ICEV, the energy source is purely gasoline, diesel, and the propulsion is purely internal combustion engine. So here are 4 different potential layouts for series hybrid, parallel hybrid, series parallel hybrid, and then some type of complex hybrid. Now, we're not going to talk about the complex hybrid as much, and now we're going to look at these 3 individual, the series parallel and series parallel hybrid, in a bit more detail. So let's look at the series. So I'm going to let you go through these diagrams by themselves, but it goes through launching or driving, accelerating, decelerating, battery charging during driving, and then just battery charging. So what are the advantages? Internal combustion engine is not directly connected to the road, so it does not need to meet all the power demand. So the internal combustion engine can operate at an optimal set point. The engine doesn't need to rev up and down. It can stay at one single RPM continuously charging the battery. So it can operate at an optimal set point, fuel economy versus power. It's also the simplest implementation. Disadvantages: it requires all the power drive from the electric motor. Therefore, you need a bigger motor. The biggest disadvantage is all the internal combustion mechanical energy is converted to electrical, then back to mechanical. Now, from anything, if you've learned from your energy conversion courses, this is bad in terms of efficiency. This is not good. Also, we need a generator and electric motor, which, given that the electric motor is driving everything, they need to be big, heavy. So yes, this is the simplest, but it's not the most efficient by any means. What about parallel hybrid electric vehicles? So this is where the engine or the electric motor, internal combustion engine or the electric motor, can drive the wheels independently. The advantages: the most power delivered mechanically, avoiding conversion losses. So the internal combustion engine delivers it right to the drive wheels. we get peak performance from both drivers. So in other words, we can drive both the internal combustion engine and the electric motor at the same time, giving an even higher peak performance. So a lot of hybrid vehicles that are performance oriented use parallel hybrid operation. I believe there was a Ferrari that was a hybrid electric that just was introduced that was somewhere near 900 horsepower when you consider the contribution from the internal combustion engine and from the electric motor. We also only need one generator, so this electric motor is needed. Disadvantages, well, engine doesn't always operate at optimal conditions because it's driving the wheels directly. We still need a mechanical gearbox / transmission, and it's a more difficult implementation. Now, series parallel hybrid operation, I think you can probably figure out what the advantages are. So optimum engineering operating point at all times, increased efficiency as most power delivered to the wheels and not stored. Charging is possible even when the vehicle is stationary, and the combined torque of internal combustion engine and electric motor. Disadvantages, as you can imagine, is the complexity of complex implementation, i.e. cost, and the control system. So higher upfront costs, but basically it has all the advantages of the other two implementations. So this is in terms of most beneficial, series parallel hybrid is probably the way to go. Now, there's different implementations depending on if you're looking at an engine heavy situation or potentially battery heavy situation. I'll let you go through these diagrams on your own time. Now, so that was engine heavy, this is motor heavy and what it might look like. Again, I encourage you to look through these on your own time. And the last thing I want to talk about in this lecture is the fuel cell. Now, the fuel cell is basically a way to replace the internal combustion engine or plugging in your vehicle. It's the way of generating the electrical power. So a fuel cell is a device that creates electrical current directly from chemical reactions. So in a chemical reaction, we get current. The polymer electrolyte membrane, or PEM, fuel cell is the most common. So briefly what happens is reactants are delivered to the anode / cathode, where only hydrogen passes through the membrane and loses electrons. These hydrogen ions subsequently combine with oxygen gas to form water. So we get these hydrogens going through this membrane, it loses some electrons, and then the hydrogen becomes water. So the only emission from a fully properly operating fuel cell is water. And that's kind of ideal when you think about it. Water is not toxic to any form of life that we know of, and it's not producing any CO2. That's great. Now, remember we said we still have to create the hydrogen, which is a problem. Creating the hydrogen probably releases some type amount of CO2. There's people who are trying to work on how that can be done more effectively. How can we take our fossil fuels and extract the hydrogen and leave the carbon in a more useful form? But that's an area of research. More power requires more fuel cells, so we need a fuel cell stack. The fuel cell itself is not governed by a Carnot efficiency, i.e. they do not operate on a cycle. So theoretical efficiency is 100%, although we are very far from that right now. Why are we far from that? Because the main issues are effectively transporting reactants and products to and from the membrane. So we said delivering reactants to the anode cathode and passing through the membrane is an important process. Well, it just happens to be the most important process is also not very efficient in fuel cells right now. Therefore, their efficiency is nowhere near 100%. There's also, as you said, the issues of how do we manufacture and store the hydrogen. If you remember an old blimp called the Hindenburg, if you've never heard of it, please look it up. That's the Hindenburg. It was a hydrogen-powered blimp that caught on fire and was quite a disaster. Now, obviously, people want to avoid that, so it's how do you store the hydrogen in your vehicle without driving around in a bomb. Hydrogen is very explosive, very flammable. If there was an accident, hydrogen leak, and there was a spark, well, there would be a very big explosion. So it's how do we store this hydrogen safely on the vehicle, and also how do we make it. So if we don't have the hydrogen, well, the whole idea of fuel cell is kind of out the window. Now, fuel cells in vehicles, essentially the fuel cell just replaces the component that generates the electrical energy. So it replaces either the internal combustion engine or the plug from the wall. And so basically you can think of a fuel cell is a way of driving around with your own little power plant that doesn't emit carbon dioxide. So it is quite a very cool idea if they can get it to figure out the transport issues and figuring out the manufacturing and storage of hydrogen. It's actually, if this was to work, this is by far the most, how shall you say, slam dunk or obvious answer in terms of solving all the technical issues that we discussed about with electric vehicles. But again, very far off. There's many technological issues, not only with the fuel cell itself, but with getting and storing the hydrogen. Okay, so I want to do a bit of a summary of, hybrid, electric, which one is going to dominate. So pollution, so why are we looking at electric and hybrid? Now, we talked about this very briefly at the start of the lecture, but let's look at that again. So he said pollution and climate change impacts, we want to reduce them. So although remember, we must consider the source of electricity and life cycle of the battery. So hybrid increases efficiency of internal combustion engine. This is really important because in isolation, most everything that can be done to increase internal combustion engine efficiency is already done. We've already looked at downsizing internal combustion engines. We've already looked at turbocharging them. We've already looked at looking at variable cam timing. So all the things can be easily done to an internal combustion engine to improve its efficiency, it's already done. There's not much more that can be done to improve the efficiency of internal combustion engine, because in the end, it's run on a cycle. And we all know you can't pass the cardinal efficiency of a cycle. So most things in internal combustion engines are already done. So a hybrid would be a way to push an internal combustion engine beyond the cardinal efficiency, because we'd actually be recovering the energy during braking. Now, electric vehicles, if charged from a renewable energy source, has the potential to be carbon neutral. Again, if you ignore the battery and the life cycle of the battery. Lower cabin and traffic noise, reduce noise pollution, we mentioned this. And for pure electric vehicle, there's much less complexity. If you look at an electric motor and electric controller versus an internal combustion engine, there's no comparison in terms of which is more complex. The internal combustion engine is way more complex. It also requires a lot more maintenance than the electrical components. The electric motor and electric controller should almost literally be maintenance-free for the life of the vehicle. Currently, with internal combustion engines, you need an oil change every 5,000 or so kilometers. You need to eventually change spark plugs, belts, et cetera, et cetera, et cetera. It's very far from maintenance-free. Now, why shouldn't we have electric or hybrid vehicles? Well, it needs lots of infrastructure changes to realize the potential pollution/climate benefits. So in order to get to the potential pollution/climate benefits, we need much more renewable energy sources. So that means we need new renewable energy or nuclear power plants. This costs time and money and energy to build. We also need more charging stations. This costs time and energy. When we use energy, we emit carbon dioxide, et cetera, et cetera. So there's tons of infrastructure that needs to be changed. All the gas stations, they pretty much need to be removed and replaced with charging stations. And they need to be retrofitted or fitted with very high rate of chargers so you don't have to take a 30-minute stop to charge your vehicle. So there's lots of infrastructure. There is some rough calculations done for British Columbia trying to achieve or trying to ban the sale of internal combustion engine vehicles by, I believe it was 2040 or 2050. If they want to do that and they want everyone driving an electric vehicle, I believe it was something where they need to build a nuclear power plant one a year for the next until 2050 or 2040, whatever that is. Well, that's not going to happen. That's just impossible. There's not enough renewable energy sources in the whole entire world to power the electric vehicle needs of just British Columbia. So you can see there's quite a big issue. So then if you fall back on what's your default, well, burn more coal. And then we're at the problem again of then we have coal-powered vehicles. So this is a huge barrier to everyone driving an electric vehicle. Now, of course, the fuel cell comes around and works out and we figure out how to make hydrogen in a renewable way and store it. This point is somewhat moot. Also, internal combustion engine rumble roar cannot be replaced. Again, this probably doesn't matter for most of the public, probably only for people who might be older. I'm not actually that old, but I guess I'm an old soul. But yeah, you can't replace the internal combustion engine rumble roar. So based on what I see and also talking with industry, internal combustion engines are going to dominate for a while still. Now, what does a while mean? No one really knows. It might be 10 years, it might be 40 years. It's not really certain. Then hybrids will follow. So eventually internal combustion engines, you won't, maybe in, after 10 to 40 years, you won't be able to buy a vehicle anymore that is just an internal combustion engine vehicle. It will be a hybrid. And that's going to last for a while we build up our infrastructure. Either we get better efficiency or other sources of renewable energy, we build more nuclear power plants, and once all that is in place, or the fuel cell gets figured out, then and only after then, electric vehicles will take over. So if I had to project when will everyone be driving purely electric vehicles, I'll probably be long dead. I'll probably be dead in about 40 to 50 years. I'm thinking it's more so around 2100 before everybody is in the world is driving an electric vehicle. So it is still a very long time frame. When will everyone be driving a hybrid? I think it'll probably be more so on the order of 20 to 40, maybe 50 years. So everybody's saying that the internal combustion engine is going to die tomorrow. That's very overstated. I 100% agree with them that the market share of internal combustion engines is going down, and people who are thinking about their long-term careers, maybe over the next generation, so maybe not us currently in engineering, but those who are coming our generation after, have to seriously consider the shelf life of becoming an internal combustion engine engineer. But for currently people who are near graduation of this generation, meaning the next 30 years, these companies are still going to need internal combustion engine engineers. Although I must admit, a much continually reduced amount of them as the shift from internal combustion engine to hybrids and then hybrids to electric vehicles occur. Oops. So ticket out the door, something you learned today, and something where the explanation was not clear or confusing. Thank you very much for watching this lecture, and we'll see you next time. Goodbye.